We present GraphDreamer, Compositional 3D Scene Synthesis from Scene Graphs. Consider the task of text-grounded 3D generation with text-to-image diffusion models. To repurpose an image diffusion model for 3D, one can optimize randomly sampled 2D views of a 3D object so that these views match the input text description. The 3D consistency of these 2D views is typically ensured by using a proper 3D representation, such as a signed distance function. While existing methods can achieve impressive results by taking as input a plain text description, they consider the scene as a whole, and the text descriptions are often simple. What if we want the scene to be compositional, allowing for editing on an object basis? What if we want to accommodate more objects, each with a well-defined description? Suppose we want to generate a 3D scene like this. One may use plain text to describe each object with their relationships. If we want to further customize each object with individual attributes, the text description grows even longer. The problem with grounding image generation in a very long and complicated text description is that the results often suffer from attribute confusion, failing to ground attributes to the correct object, and guidance collapse, where some content in the text is ignored or misinterpreted. These are inherent problems caused by text-image embeddings and thus affect all methods using plain text for grounding. Good thing is, the desideratum being compositional is itself a way to address these problems. A straightforward solution to compositionality is to explicitly position objects within a set of 3D bounding boxes. Objects are modeled separately with individual descriptions and then composed together based on the 3D layout. While this approach enhances the ability to accommodate more objects, it relies on the restrictive assumption that there is no overlap between object boxes, which often does not hold in practice. Our main insight is that a scene graph, with its nodes and edges clearly defining objects and their relationships, offers a semantically more precise representation of a scene. It does not rely on the restrictive no-overlap assumption associated with bounding boxes, but instead inherently possesses the property of decomposability, allowing it to be readily broken down into subgraphs. For example, we can use the node along with all its attached attributes to describe an object. And an object relationship is a subgraph with two nodes connected by an edge. These subgraphs can be easily converted back into text, allowing us to embed graphs into the aligned latent space used by text-to-image diffusion models. Given the scene graph representation, we can optimize a proper scene decomposition by supervising the decomposition jointly at the object level, edge level, and scene level, constraining it to satisfy all the individual attributes and the relationships between objects as described. Our method achieves state-of-the-art quality, object compositional generation, and higher semantic accuracy without imposing any restrictive assumptions on object relationships. Performing decomposition before rendering is essential because, when multiple objects obstruct each other, we need to make the obscured surfaces visible to model the objects completely. To achieve a proper decomposition, the underlying 3D space must be decomposed on a point-by-point basis. Since a point can be occupied by at most one object, it is possible to assign each point in the 3D space a unique identity. To this end, we choose a signed distance function as the 3D representation because it provides clear object boundaries along with inside-outside information. Our key design is to encode each point in the 3D space not as a single positional feature embedding, but rather into multiple feature embeddings using a set of encoders, corresponding to the number of objects. Assume there are M objects in the scene. These M feature embeddings are then passed to shared shallow MLPs, yielding M pairs of SDF and color predictions. Since these MLPs are shared and shallow, using multiple encoders allows each encoder to focus on one object exclusively, enhancing the capability to identify each point. Now, based on these SDF predictions, we can identify a point as belonging to object J if its SDF value is minimized at index J. We thus predict a one-hot identity vector for each point in the space, where the index of the non-zero element indicates the object to which the point belongs. Using these identity vectors, we can directly decompose the scene into individual objects. In practice, we combine these three levels of supervision in a memory-efficient way. As we show in our paper, an additional geometry constraint is also needed to account for unobserved spatial locations, such as inside objects and surfaces at object intersections. In summary, we propose a graph-grounded generation method to transform semantic descriptions into 3D scenes, while keeping each object separable, without imposing any restrictive assumptions on their relationships. We showcase improved semantic accuracy when applied to complex scenes involving multiple objects with specific attributes and mutual relationships. Thank you for listening, and please refer to the paper for more information and results.